I am in Ramya, Department of Mathematics. My topic, the residue theorem and the residue evaluation. First we see residue theorem. Consider a line integral about a path enclosing an isolated singular point I equal to integral over C f of z dz. Expand f of z in a Lorentz series. Deform the contour C to a circle of radius r centered at z0 that stays inside C and evaluate the integral using the Lorentz series formula. F of z equal to summation n equal to minus infinity to infinity a n z minus z0 whole power n. Here z minus z0 equal to r e power I theta, dz equal to r I e power I theta into d theta. The path C stays in a region where f is analytic except at z0. So we know integral over C f of z dz equal to I into summation n equal to minus infinity to infinity a n r power n plus 1 integral 0 to 2 pi e power I into n plus 1 theta d theta. Here evaluate this integral equal to I a minus 1 r naught 2 pi. It's by Lorentz expansion, that is equal to 2 pi I a minus 1. Here for Lorentz series we can integrate term by term in the region of convergence due to the uniform convergence. The value a minus 1 corresponding to an isolated singular point z0 is called the residue of f of z at z0. Here I equal to integral over C f of z dz equal to 2 pi I residue of f of z0. This is the formula. Note the path orientation is assumed counterclockwise. Here the Lorentz series expansion is here f of z equal to etc. a minus 1 divided by z minus z0 plus a naught plus a1 z minus z0 plus etc. Here this a minus 1 is the residue. Extend the theorem to multiple isolated singularities. Integral over C minus summation Cn f of z dz equal to 0. Integral over C f of z dz equal to summation n integral over Cn f of z dz. Here summation 2 pi I residue f of zn. 2 pi I into sum of residue. Alternatively, integral over C f of z dz equal to summation n integral over Cn f of z dz, that is equal to 2 pi I summation residue f of zn. Summary of residue theorem. A function f is an analytic within C except at isolated singularities. The isolated singularities at zn is shown in figure. Integral over C f of z dz equal to 2 pi I summation n residue of f of zn. The integral is equal to 2 pi I times the sum of residues at the singularities. Note the integral is taken counterclockwise. Next we see Cauchy's theorem. Integral over C f of z dz equal to 0 if f of z analytic, no isolated singularities in C. Cauchy's integral formula. Integral over C f of z divided by z minus z0 dz equal to 2 pi I f of z0 if f of z analytic in C. Hence z0 is the only isolated singularity in C. Note f of z equal to summation n equal to 0 to infinity bn z minus z0 whole power n. This implies f of z divided by z minus z0 equal to summation n equal to 0 to infinity bn z minus z0 whole power n minus 1. This implies residue of f of z divided by z minus z0 equal to b0 equal to f of z0. Evaluating residues. Construct a Lorentz series about each singularity zn and then identify the coefficient a minus 1 n equal to residue f of zn. Sometimes this can be deduced approach. For a simple pole at z equal to z0, we have the simple formula limit z tends to z0 z minus z0 f of z equal to limit z tends to z0 z minus z0 into a minus 1 divided by z minus z0 plus a0 plus a1 into z minus z0 plus etc. Here residue of f of z naught equal to limit z tends to z naught, z minus z naught into f of z. Examples: f of z equal to 2z divided by z plus 2, z square plus 1 has simple poles at z equal to minus 2 plus or minus I. First we find residue at f minus 2. Residue of f of minus 2 equal to limit z tends to minus 2, z plus 2 into 2z divided by z plus 2 into z square plus 1. Here z plus 2 and z plus 2 cancel. We replace z equal to minus 2. So we simplify this equation, we get minus 4 by 5. Next we find f of I. Residue at f of I equal to limit z tends to I, z minus I into 2z divided by z plus 2. Now expand z squared plus 1 the factors, z plus I into z minus I. Here z minus I and here z minus I cancel, remaining we replace z equal to I. Finally we get the answer 2 minus I divided by 5. Next to find f of minus I. Residue f of minus I equal to limit z tends to minus I, z plus I into 2z divided by z plus 2, z minus I, z plus I. Here z plus I cancel. Finally we get the answer 2 plus I divided by 5. Next example, f of z equal to 1 by sin z has simple poles at z equal to n pi, n equal to 0 plus or minus 1 plus or minus 2 etc. Residue f of n pi equal to limit z tends to n pi, z minus n pi into 1 by sin z. Using L'Hospital rule, limit z tends to n pi 1 by cos z, that is equal to minus 1 whole power n. Alternatively, residue f of n pi equal to limit z tends to n pi, z minus n pi into 1 by sin z. Next, add and subtract n pi, 1 divided by sin z minus n pi plus n pi. So expand this trigonometry formula, limit z tends to n pi, z minus n pi into 1 divided by sin z minus n pi cos n pi plus cos z minus n pi sin n pi. So we replace z equal to n pi, z minus n pi divided by sin z minus n pi cos n pi, that is equal to minus 1 whole power n. Previous rule can be specialized to functions of form f of z equal to n of z divided by d of z, where d of z has simple pole at z naught, simple 0, d of z equal to a1 z minus z naught plus a2 z minus z naught whole squared plus etc. Residue f of z naught equal to residue n of z divided by d of z at z naught. So finally we get n of z naught divided by d dash of z naught. This is fraction formula. This, for example, f of z equal to tan z. Tan z equal to sin z divided by cos z has simple poles at z equal to 2n plus 1 pi divided by 2 for n equal to 0 plus or minus 1 plus or minus 2 etc. Residue at tan z equal to sin 2n plus 1 pi divided by 2 divided by minus sin 2n plus 1 pi divided by 2. So this cancel. Finally we get the answer minus 1. Residue of tan z equal to minus 1. That is z equal to 2n plus 1 into pi divided by 2, n equal to 0 plus or minus 1 plus or minus 2. Thank you.